This is Math 131, Section 5.6. We're first going to talk about exponents. Okay, and the first rule of exponents we're going to talk about. And remember, exponent is repeated multiplication. So the product rule for exponents, let's say we're looking at 2 squared times 2 cubed. Okay, now that means 2 squared means we're multiplying 2 times. Okay, and then we're multiplying it 3 more times. Okay, and then we're multiplying. Okay, so if you do that, we're actually multiplying 2 times plus 3 times. So we just add the 2 here and the 3 here, the exponents, to get the 5. Okay, so that's called our product rule for exponents. Okay, so just in general form, if we have a to the nth power times a to the n power, we're just going to add the m and the n and keep the a the same. Okay, we had 2 as our example before. Okay, so if you're multiplying for our base, but here our base, let's say it's any number, it could be any real number, then if you have the same base, you just add the exponents m plus n. That's called our product rule. Okay, so first example, 3 cubed times 3 squared is just 3 to the 3 plus 2. We add this 3 and this 2 to get 3 to the 5th. And if you multiply 3 5 times, you get 243. And remember that 3 to the 5th is, 3 times 3 times 3 times 3 times 3. Okay, and if we multiply that out, 3 times 3 is 9, times 3 is 27, times 3 is 81, times 3 is 243. So that's our 3 to the 5th there. Okay, now let's talk about our quotient rule. So when you're dividing exponents with the same base, let's look at 2 to the 5th divided by 2 squared first as an example. So 2 to the 5th is 2 times 2 times 2 times 2 times 2. 2 squared is 2 times 2. And what you can do here when you're dividing is you can cancel out 2's on the top and the bottom. So divide by 2, and then we can do another one, right? Okay. So really what we're doing is we're taking that 5 and we're subtracting out the 2 because 2 of those cancel. And we end up with 3 2's. So 5 minus 2 is 3. So this gives us 2 to the 5 minus 2, which is just 2 cubed, 2 to the 3rd. Okay, and that gives us our quotient rule for exponents. So our quotient rule is if you have a to the m and divide by a to the n, then you get a to the m minus n. So you just subtract those exponents and keep your base the same. Now here we have to say that a cannot be 0 because you're dividing by a, right, to the nth power. So you can't have 0 in your denominator. That's why we say a is not equal to 0 there. Okay, so let's look at a couple examples using quotient rule. 3 to the 7th or to the 3 to the 5th is 3 to the 7th. Sorry, that should be 3 to the 7th minus 5. So let me rewrite that. This should be 3 to the 7 minus 5. Okay, not that. And this should be 5 to the 9 minus 5. Okay, so we're subtracting the exponents here. So 3 to the 7 minus 5 is 3 to the 2. Got to fix that too. Equals 3 squared, which equals 9. Okay, and this equals 5 to the 4th, which is 625. Sometimes these exponents don't come out in these slides very well. So, okay, so here we're taking 7 minus 5 to get 3 squared, which is 9. And here we're taking 9 minus 5 with our base of 5 to get 4. Okay, and 5 times 5, remember 625. 5 to the 4th is 5 times 5 is 25. Times 5 again is 125. Times the 4th 5 is 625. So that's just multiplying 5 4 times. Okay, our 0 exponent rule says anytime you take something to the 0 power, whatever the number is, it's going to be 1, unless it's 0, right? Okay. So if it's non-zero, if it's any number that's not 0, you take it to the 0 power, you always get 1. Okay, so here's an example using our 0 exponent rule. 2 to the 0 is 1. Minus 2 to the 0 is 1. Now when you have parentheses, that means this is your base. So your base here is minus 2. Now be careful when you don't have parentheses, because here your base is really just the 2, okay? So a good rule of thumb for exponents is if there are no parentheses, you can only use one character as your base. So here my base is just 2, it's not minus 2, okay? So really this is minus 1 times 2 to the 0, okay? And then this 2 to the 0 is 1 over here, so we actually get minus 1 times 1, which is minus 1, okay? So notice the difference between B and C here. Here our base is minus 2, and we take anything to the 0 power, we get 1. But here my base is just 2. Okay, the negative is not part of my base. Okay, because I don't have parentheses. Okay, and then same with D and C. Here 5x is my base. Okay, so 5x to the 0 is 1 because I have the parentheses. But here my base is just x. Okay, so this is 5x to the 0 without parentheses is really 5 times x to the 0. So this is 5 times 1, which is 5. Okay, so notice the difference here. Okay, so a good rule of thumb is this. No parentheses means base is one character. One typeset character. So base is just one character. So again, for C and E here, I have no parentheses, so my base is just 2. Okay. Here I have no parentheses, so my base is just x. I can't use the minus because that would be 2 characters. Okay. I can't use the 5 on the x because that would be 2 characters. So when you see no parentheses, it means your base is just 1 character. Okay, our negative exponent rule says if you take something to a minus power, you just take it 1 over to a plus power. Okay. A is not equal to 0 because we're dividing by a in this one. But you can think of this. Remember, exponents are complete repeated multiplication. Well, when you have a negative, it means repeated division. So this says you're dividing a m times. So let's look at an example here. Let's say I have 2 to the minus 3. Instead of saying 2 to the third, multiplying 2 3 times, I'm dividing 2 3 times. So I'm going to say 1 divided by 2, divided by 2, divided by 2, which gives me 1 half times a half, that's the same as divided by 2, times a half, which is 1 over 2 to the third. See how we kind of show that with an example where 2. See, now you're dividing by 2 3 times, means you have 1 over 2 to the third in the denominator. Okay, but if you remember your negative exponent rule, that's sufficient. Okay, a couple examples. 3 to the minus 2 would be 1 over 3 to the plus 2, which is 1/9. 7 to the minus 1 would be 1 over 7 to the plus 1, which is 1/7. Notice these do not give us negative numbers. The negative exponents do not give us negative exponents. It just means we're dividing instead of multiplying. Okay, now let's look at the power rule for exponents. That is where we're taking an exponent to another exponent. Okay, so in this case we're taking a to the mth power to the nth power. So let's look at 2 squared to the third power. Okay, now we have 2 squared in parentheses, which means this is our base. Okay, 2 squared, and we're going to multiply it 3 times. So we're going to say 2 squared times 2 squared times 2 squared. That's where the 3, we're multiplying it 3 times, right? Now we're using our product rule, and we can just add the 2's, right? So 2 plus 2 plus 2 here. So we get 2 plus 2 plus 2, or 2 3 times, which is 2 times 3, which means we can just multiply 2 times 3 here. We don't have to say 2 plus 2 plus 2. We can just say multiply the 2 times 3, and that gives us 2 to the 6, which is 64, right? Okay, in this case, that's equal to 64, multiplying 2 6 times. Okay, and then the general rule is just a to the m to the nth power, so we're taking it to 2 powers. We just multiply the 2 powers. Now notice we only have one base here because we're taking this exponent to another power. Okay, so you'll only see one base here, and here's where you multiply your exponents. Okay, that's our power rule. Okay, so let's look at a couple examples. 2 to the 4th to the 5th is 2 to the 4 times 5, which is 2 to the 20th. Okay, a very big number. Okay, 3 to the 7th squared. Now notice in both of these cases our base is in parentheses, as it should be. Okay, and then we're going to take 3 to 7 times 2, which is 3 to the 14th. Okay, so that's just applying our power rule there. Okay, and just to summarize our rules of exponents, our product rule, okay, is when we're taking 2 numbers with the same base and we're adding the exponents when we multiply. Okay, so a to the m times a to the n is a to the m plus n. Okay, our quotient rule is when we divide, so we're taking a to the m divided by a to the n. We take a to the m minus n, subtract. Okay, and we say a is not equal to 0 because it's in the denominator. Okay, our 0 exponent rule: anytime you take something to the 0 power, as long as it's not 0, you get 1. Okay, our negative exponent rule: if you take a to the minus m, it's 1 over a to the plus m. Okay, and that's also it can't be 0. And then finally, the last thing we looked at, our power rule for exponents, is a to the m to the nth power is a to the m times n. Okay, let's look at one thing before we move on, though. I want to look at this a to the minus m. Because you can do kind of, when you think of a negative exponent, you can do this. Let's say I have 2/3 to the minus 5. Okay, what you can do is you can flip your fraction, because think about what we're doing here. We're taking 1 over a to the plus m, right? So what we can do, what we're essentially doing is taking that fraction and flipping it and making it to the plus 5. Okay. Okay. So that's another thing, is that when you have a fraction as your base, if you have it to a negative exponent, just flip the fraction, you can put it to a positive exponent. So that's something that's worth recognizing there. Okay, now let's talk about scientific notation. We use scientific notation to kind of summarize numbers that are very big, okay, large or very small numbers, and we kind of do it by using kind of not all the zeros we need. We don't use all the zeros. So like, for example, the distance from the Earth to the Sun is 93 million miles. It's a large number. The wavelength of a yellow color of light, it's a very short wavelength, is 0.0000006 meters. Okay, so very small. So we use scientific notation to kind of put these numbers in kind of compact form, so we don't have to put all these zeros here. Okay, either before the number if you have a decimal, or after the number if it's a large number. Okay, so for example, we can write 93 million as 9.3 times 10 million. Okay, and then we can write that 10 million as 10 to the 7th. See, because if you think about how we write powers of 10, if you have a number like 10 million, just count the zeros, 1, 2, 3, 4, 5, 6, 7, and we can write it as 10 to the 7th. Let me give you some examples, like 10 to the 1 has 1 0, right? 10 to the 2 has 2 zeros. 10 to the 3 has 3 zeros. Okay. 1,000, right? So 10 to the 7th has 7 zeros. Okay. So we can write this, instead of writing it 9.3 times 10 million, or even 93 million, we can just write it as 9.3 with 10 zeros, sorry, with 7 zeros after the point, right? Well, we don't count that zero. So, but it's 9.3 times 10,000, and 10,000 has 7 zeros. Okay. And then we can also do the same thing with small numbers. So if we think about like 10 to the minus 1 is 0.1, 1/10, right? And you can think of it's one place after the decimal. 10 to the minus 2 is 0.01. 10 to the minus 3, 100th. 10 to the minus 3, 1,000th is 0.001. Okay. And we could say, okay, well, the negative exponents means you have one decimal place, right? It goes one place after the decimal, the 1. Here, for 10 to the minus 2, it goes 2 places after the decimal. And here, 10 to the minus 3, it goes to the 3rd place after the decimal. Okay. So we can write this second one, this small number, 0.0000006, sorry, let me change that to blue, as 6 times 0.0000001. Okay, and then, well, this number here is 10 to the minus 7th. You can see that 1 is the 7th place. 1, 2, 3, 4, 5, 6, 7. Okay, so 6 times 10 to the minus 7. Okay, so that's how we write that in scientific notation. And the big number, 9.3 times 10 to the 7th for 93 million. Okay, and here's a trick that you can do to do this. Let me kind of use, let's do the arrow first. Okay, if it's a big number, start where your decimal point is, which is right here, and you want to go so that there's one number before the decimal, one digit. Okay, so we start here and we count 1, 2, 3, 4, 5, 6, 7. So we could say 9.3 and say times 10 to the 7. So we counted 7 places. Okay, and we make that a positive if it's a big number. Now we can do the same thing with a small number. Start at the decimal point and we want to go just past the 6. So we want the dot right after the 6. We count our places. 1, 2, 3, 4, 5, 6, 7. So it's 6.0 times 10 to the minus 7. So you're just counting your decimal places as you move it either to the right or to the left. If it's a big number, you use a plus 7. If it's a small number, like a small decimal, you use a minus. Okay. In this case, they're both 7s, right? So here's kind of what we're doing is we're counting. Here we're starting at this dot right here. We're going 1, 2, 3, 4, 5, 6, 7. See, you move 7 places. Okay, and we use a plus because it's a big number. okay? And we want to make sure that there's one number in front of the dot, okay, in front of the decimal place. Okay, and we do the same thing here. Start at the decimal place, 1, 2, 3, 4, 5, 6, 7. So we got one number before the dot, so this is 7 places, but we're going to use a minus there, right, because it's a small number. Okay, so minus for small, decimal, and a plus for big. Okay, so that's kind of the rule of thumb there. There are rules in the book to follow, but I think my method is a little bit easier because you don't have to worry about whether you're moving left or right. So I'm not going to cover that in the lecture here, but read that in the section. If it's easier to remember that, then do that. But kind of I'll go over this in class too. But basically, we're just counting as we move the decimal, and then if it's a big number, we use that as a positive, and if it's a small number, we use it as a negative. For we don't care which way we move left or right because we just look at how big the number was when we started. Okay. Okay, so let's look at a couple examples. 1 drop of blood contains about 5,800,000 blood cells. That's a lot. Okay, so we write that in scientific notation. So here's our decimal, and we want to move it over here, right, just after the 5. So we move it 1, 2, 3, 4, 5, 6 places. So now we get 5.8 times 10 to the 6, okay, because it's a big number, so we use a plus 6. Okay. In 2014, there were about 310,600,000 personal computers in the United States. There's probably a lot more now. Here's our decimal. So let me just show you what we do with the decimal here. So here's our decimal, right? And we moved it 1, 2, 3, 4, 5, 6 places, right? Okay. So we're going to say plus 6. 5.8 times 10 to the plus 6. Okay. So there's our number. Okay. And then here we're starting here with our decimal here. So we get 1, 2, 3, 4, 5, 6, 7, 8. We wanted to stop just before the last number. Okay. So we moved to 8 places, and that's going to be a plus 8 because it was a big number. So this would be 3. Now we have to use the whole number here that we have. If there's a 0 in between, so we got to use all of this, right? We don't need the zeros after that. So we'd be 3.106. See, because our decimal ended up right there, right after the 3, times 10 to the plus 8. Okay. Let me see how we got that. Kind of using the method I showed you. Okay, C. In 2014, the population of the world was about 7,263,000,000. Okay, so here's our decimal. We move 1, 2, 3, 4, 5, 6, 7, 8, 9. We stop just before the 7. Okay, there's our dot now. So we have 7.263, and we moved it 9 places, and it's going to be a plus 9, right? So we put plus 9 there. Times 10 to the 9th. Okay, so that's how we got that. And now let's look at a small number. So our dot is here, right? We want to end up in between the ones. So we're going to go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay, to end up right there in between the ones. That's a minus 12, right? Because we started with a small number. So we're at 1.1 times 10 to the minus 12. So you're basically just counting, how many places you're moving the decimal. Okay. And put that in there, but make sure you're putting the decimal so that you have 1 digit before the decimal only. Okay, 1 digit. Okay, before the decimal. Okay, last example. The wavelength of an X-ray is about 0.00000000049 meters. Okay, we want to be between the 4 and the 9, so we start here at the decimal. Go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 places. Okay. That's going to be a minus 10, right? So we have 4.92 times 10 to the minus 10. Okay. Remember, we want to have 1 decimal place, 1 number before the decimal. Okay. When we get at our final destination. Okay, so let's talk about changing a number that's in scientific notation to a regular decimal number. Okay, to decimal notation. Okay. First thing we do is observe the exponent on the 10. Okay. If the exponent is positive, move the decimal point to the right that many places. Adding zeros might be necessary. Okay. So if it's positive, we move it to the right. Okay. If the exponent is negative, we move the decimal point to the left, however many places it says. And we may have to add zeros again. Okay, so if it's negative, we move to the left. Okay. Okay, so let's look at an example. For A, the average distance from Mars to the Sun is about 1.4 times 10 to the 8th miles. So we start with our 1.4, and we're going to move it 8 places to the right. Okay, so we're going to go 1, 2, 3, 4, 5, 6, 7, 8. Now we'll put our dot there. We have to add zeros. So we have to put a 0 there, 0 there, 0 there, 0 there, 0 there, 0 there, 0 there. Okay. And then as you go backwards from the decimal, you can go by threes, right? To you put your commas. So 3, comma, 3, comma, gives us 140 million. Okay. Okay. And then B, the half-life of uranium-235 is about 4.5 times 10 to the 9th years. Very long time. Okay. So we're going to start at 4.5. We're going to go 9 places to the right. 1, 2, 3, 4, 5, 6, 7, 8, 9. Put your decimal there. Fill in zeros where you need to. Okay. Make sure you are neat so you get every spot, right? Okay. And then we can put our commas as we go backwards from the decimal. So 3 there, 3 there, 3 there. Gives us about 4 billion, 500 million, or 4.5 billion. Okay. Years. Okay, C, the average grain size in siltstone is about 1.35 times 10 to the minus 3 inches. So now we're going to move to the left. So we start at 1.35 and we're going to go 1, 2, 3 to the left. Put your decimal there. And then fill in zeros where you need to. We need to put in 2 there, right? So it would be 0.00135 inches. Right? Okay. And then a millimicron is a unit of measure used for very, very, very small distances. 1 millimicron is about 3.94 times 10 to the minus 8th inch. So we start at 3.94, we're going to go 8 to the left. So we're going to go 1, 2, 3, 4, 5, 6, 7, 8. Okay. So our dot goes right there, and we fill in zeros. So we got 1 there, 1 there, 1 there, 1 there, there. Okay. So it's 0.000000394. 7 zeros, right? It should be 7 there, okay, in front of the 394. Okay, so there's how small that decimal number is. Okay. Okay, another way we use scientific notation is if we're adding or multiplying numbers, well, multiplying generally, is it's much easier to multiply numbers, big numbers and small numbers using scientific notation, because once you have in scientific notation, you can regroup them. Let's say we have 2.1 times 10 to the 5th, which is a really big number, and we have 9 times 10 to the minus 3, which is a really small number. Well, what we can do, remember our associative property of multiplication is saying if you're multiplying a bunch of numbers, you can move them around. So we can move the 10 to the 5th over here and the 9 over here, so we've got the 9 and the 2.1 together, and then the 10 to the 5th and the 10 to the minus 3 together, okay? So we're going to put our powers of 10 together and our other numbers together, okay? And then 2.1 times 9 is just 18.9. And then remember with exponents, if you're multiplying, you just add the exponents, right? 10 to the 5th times 10 to the minus 3 is 10 to the 5 plus or minus 3, which is 2. So 10 squared, okay? So we have 18.9 times 10 to the 2, okay, when we regroup, okay? Now we want to put it in scientific notation, okay? So we don't quite have it where we want it, right? Because we don't want the decimal place here, okay? We want it over here, so we're going to move it over 1, okay? Now think about what we did there. When you move it over 1, to the left, you're dividing by 10, which means you have to multiply by 10 over here, okay? See, because we shouldn't have really moved it over 1, but we had to, right? So when you move it to the left 1, you're dividing by 10, which means you'll multiply by 10 to undo that, okay? And that's how we get that 10 to the 3rd, because we're multiplying 10 squared times 10 to the 1. And that's how we get 1.89 times 10 to the 3rd. Okay, it's a little tricky at first, but we'll look at some examples in class. And then decimal notation, we're just doing this. 10 to the 3rd, we move this over 3, right? And that's how we get our 1890 there. Okay, to put it in decimal notation. Okay, so when we're multiplying numbers in scientific notation, basically we're grouping, so it's much easier than if we had to multiply them without scientific notation. Okay, now let's divide numbers in scientific notation. Again, this is a very useful tool to have, because to divide this would be kind of a pain, but if we make the scientific notation, now let's do this one. Okay, so this is where we have to move it to between the 4 and the 8. So we're going to move it 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 places. So this is 4.8 times 10 to the minus 11, right? Because it's a small number. Right? Okay. And then here here are dots here. We want to put between the 2 and the 4. So we're going to move it 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 places. So this bottom one is going to be 2.4 times 10 to the plus 10. Okay, so that's how we get our scientific notation for each number. Okay, now we're dividing. We can kind of group these together, the 4.8 and the 2.4, and then the 10 to the minus 11 and the 10 to the plus 10. Okay, so we can say, okay, let's divide the 4.8 and the 2.4, and that gives us 2, right? And then remember, when we're dividing exponents, we subtract. So this would be minus 11 minus 10, which is minus 21. Okay. So minus 11 minus 10. So we end up with 2.0 times 10 to the minus 21. Okay, so that's our scientific notation version of that problem. Much easier than we have to do this division, kind of longhand without scientific notation. So it's a very useful tool to use this sort of notation when we're dealing with very large numbers and very small numbers, and we're trying to multiply or divide them or whatever. Okay, so we'll look at some examples in class. We're doing this, and also, with that previous slide, we'll look at some adjustments too as examples.